everyone. Today I'll talk about how to solve contextual linear bandits using linear bandit algorithms. This is a joint work with Professor Lin Yang and my advisor, Professor Cristina Fraguli. I'm sure most of you know about bandits, but just to review it and for notation purposes, let's quickly overview the setup. So in multi-arm bandits, a learner interacts with an environment by pulling arms from a set of arms and then receives a reward that's sampled from an unknown distribution with unknown mean. So the learner sequentially interacts with the environment and observes rewards. At each time slot, the learner's arm is a function of the history that the learner observes, which is the sequence of both the actions and observed rewards. And the objective of the learner is to maximize the sum rewards on average or equivalently minimize the regret, which is the difference between expected rewards drawn from the best arm minus the arms that the learner actually pulls. Linear bandits is a special class of bandits in which the action set is a subset of RD, and the means of each arm is has this linear structure. So the mean of arm AT is the dot product of AT and some unknown parameter theta star, and then the reward observed by the learner is this mean plus some noise. That's zero mean sub-Gaussian conditioned on the filtration of history. This is known to be a generalization of the unstructured finite arm bandit model, and it has many applications. It's very well studied in theory and practice. For example, a quick search on Google Scholar for the past 2 years show more than 10,000 publications on linear bandits. However, there is one aspect that this problem doesn't capture, which is the context of a user. For example, if we are deploying bandits in recommendation systems, we may not want to recommend the same product to all users, but we may want to tailor our recommendation based on information about the user, like age, location, or past interactions with the system. This is a side information that's observed by the learner at each time slot, and it's referred to as the context. And the model of contextual linear bandits is that the learner observes a context CT at time t, and there is a known feature map phi that takes as input the context at time t, the picked action by the learner at, and then transforms this to a d-dimensional vector, and the mean of the reward is linearly parameterized by that output vector. It's well known that this problem can be rewritten as exactly linear bandits, but allowing the action set to change over time, where this changing action set AT is now the collection outputs of the collections of outputs of the feature map phi at the current context CT. Okay. So the challenge in this problem is that this changing action set makes the problem harder to solve than linear bandits, and this is reflected in the regret bounds in the literature. So the regret bounds for linear bandits are usually tighter than those for contextual bandits in many setups, and in some setups, for example, we are able to achieve only in expectation regret bounds as opposed to high probability bounds for linear bandits, where by a regret bound in expectation we mean that the expected regret is upper bounded by some quantity, and the high probability bound means that the regret is upper bounded by this quantity with high probability. So the high probability bound is a stronger result because the expectation may be tightly bounded but the variance can be very large. And to understand why this is the case, so let's quickly think of one way to solve linear bandits. So the only unknown variable in this problem is theta star. If we perfectly know theta star, then we can perfectly solve the problem and incur zero regret. Uh, so let's think about how to learn this theta star. So in some cases, the action set may not be very diverse. So if we factor this theta star, for example, into two components here, theta 1, theta 2, as we can see, theta 2 is almost perpendicular to the directions of all actions in the action set. So it may be challenging to estimate this component theta 2 in the presence of the noise. But as we might think, also it doesn't affect the reward means that much. So if we learn theta 1, maybe that's good enough. And that's what some algorithms for linear bandits do. If you're familiar with, for example, phase delimitation with the G-optimal design, that's basically what it does. But such algorithms are harder to implement for contextual bandits. And that's because the directions in contextual bandits change over time. So, for example, at the first time slot, we may have this action set here. At the second time slot, the action set can completely change. Despite this, we show in one of our papers that if the contexts are generated from a distribution, then we can actually reduce contextual linear bandits to linear bandits. And more specifically, we prove the result in two steps. So first, we show that if the context distribution is known, then we can reduce any contextual bandit instance to a linear bandit instance. And we show that if the context distribution is unknown, then we can reduce every contextual bandit instance to a sequence of log t linear bandit instances, where t is the time horizon. Okay, so so briefly, what we are gonna do is, instead of solving the contextual bandit linear bandit problem with action set that changes over time, we will reduce that to a linear bandit problem with action set that's fixed over time. We will use any linear bandit algorithm to solve the reduced problem, and our reduction will carry out the solution to the original problem. Okay. So that's the main idea, and in the following, I will explain the details of how to do this. So first, let's see how we construct this fixed action set X for the linear bandit problem. We consider this function g of theta. It takes as input one unknown parameter theta. So it's a d-dimensional vector. And what it does is that it outputs the expectation of the best action with respect to that input parameter theta. And the expectation is taken over the context distribution. So g of theta takes a d-dimensional vector. This argmax for each context outputs a d-dimensional vector. We take the expectation over that. So it's from RD to RD. Okay, and our set of actions is the collection of outputs of this function for each theta in the unknown parameter set. So that's our fixed action set. Let's go
Sorry, can
through.
I ask a quick question there? Um, what do you do if there are more than one arm that achieve the maximum there?
Yeah, that's a good question. So we basically show in our paper that if you use any choice function, then it will work. So just choose some choice function, fix it, and it will work.
Okay, thank you.
We can break ties arbitrarily, basically. Yeah. Thank you for the question. Okay. So go through some one example on how to compute this function g and the fixed action set. So let's say that we have two possible action sets, a1 and a2, at each time slot we get either A1 or A2 a uniformly at random independently from other iterations, and we have only two possible unknown parameters, either theta 1 or theta 2. Okay, so how to compute, for example, if we want to compute g of theta 1, the best action in the first action set is A2 that has the maximum dot product with theta 1, and in the second action set it's A2 tilde. So g of theta 1 is the average of A2 tilde, and it will be something like what's shown here. If we want to compute g of theta 2, same thing, the action that has the maximum dot product in the first action set is A1, the second one is A1 tilde, and g of theta 2 is the average of these two actions, so it will be something like what's shown here. And if the unknown parameter consists of only theta 1, theta 2, then our fixed action set is the collection of g of theta 1, g theta 2. So that's how we compute this function g of theta, and therefore the fixed action set. Now let's go through how the reduction will work. So the learner, as we said, will use any linear bandit algorithm. It will draw actions from the fixed linear bandit action set X. So let's say at time slot t, the bold action is xt. Because of the how we construct this fixed action set X, this xt is equal to g of theta t for some theta t. So what we do is that we will take this theta t, and we will play the action that maximizes the dot product with this theta t in the current context. So xt is an artificial action. It may not even be feasible, but then at, which is the argmax over the current context, this is a feasible action. Okay. So we will play this at. The environment will generate some reward from the true action at, and we will provide this reward to the learner, and the learner will proceed assuming that this reward was actually generated from the bold action xt or g of theta t. So this assumption may not be correct, but the learner will assume this and continue learning, ignoring any details about the contextual bandit problem. Okay, so that's how the reduction works. So let's try to quickly see how why this results in a small regret. So if we use a good linear bandit algorithm. So first, we show in our paper that the learner's assumption, which is that the rewards follow a linear bandit model with unknown parameter theta star, is actually correct. So RT can be expressed as the dot product of g theta t and the same unknown parameter of the original problem plus some noise. And this noise is zero mean and sub-Gaussian when we condition on the filtration of history. And the history here is the history of interaction for the linear bandit problem. So it's the sequence of bold actions, the actions g of theta t, and the observed rewards rt. So that's the first thing we show. And the second is that the best action in the reduced space is actually g of theta star. And we show that this leads to that the difference between the regret of the linear bandit instance and the contextual bandit instance it forms a martingale with bounded difference. So it's bounded with square root t log t with high probability. Okay, so this is how our reduction works for a non-context distribution. And the reason we say non-context distribution is that we need to compute this function g of theta, and this function is an expectation over the context distribution. So if we don't know that distribution, we may not be able to compute this function g. Okay. So what do we do in that case? A natural idea is to estimate
Oh,
this.
sorry, a quick question. In the previous slide, your expectation is over arms at 80, but it's conditioning on 80 at the same time?
Ah, yeah, I'm sorry about this. This is a typo. Yeah, this is a typo.
Oh, okay.
Yeah, it's the conditioning is on theta.
Okay, okay, okay. Yeah.
Yeah. Yeah. Thank you for noticing this. So one natural idea to extend this is to estimate this function g by sampling from the context distribution. So how do we do this? So our algorithm in this case works in epochs of exponentially increasing length. Uh, and in each epoch, we use the observations of previous contexts, the contexts in previous epochs, to estimate this function g. So in epoch at the start of epoch m, our estimate is this function gm, and in this case we just imagine that this function gm is the true g, and within the epoch we basically do the same reduction as in the known distribution case. Um, this creates a problem here. So now when we use the function g with gm, the learner assumes that the mean of each arm follows this linear structure with the action equal to gm of theta t. But this is actually not correct. This is true with the true function g. So this is what's called a Messi-specified linear bandit instance, and by this we mean that the reward is deviate from the linear structure by a function of the action f of a, and the magnitude of this function is upper bounded. Okay. And to show that our reduction works in this unknown distribution case, we need to show that the amount of misspecification is small. So this is the first step in our proof. But can we guarantee this for all unknown parameters? It may be hard if the unknown parameter set is large or even infinite. Then it's hard to guarantee this for all unknown parameters. So our fix for this is to use the standard idea of epsilon net. So we consider a discretization, a fine discretization of the unknown parameter set, uh, and we can guarantee that the misspecification is small over the discretized set using a union bound argument. So this discretization creates some problem. We don't know theta star, so this discretization may eliminate theta star. And as we said previously, the best action in the linear bandit instance is g of theta star. And the problem is that this function g is not Lipschitz, which means that a small change in the input may result in arbitrary large changes in the output. So even though the discretization provides with another unknown parameter that's close enough to theta star, but this property of G that it's not Lipschitz may cause that theta to not work. But what we show in our paper is that even though G is not Lipschitz, it's actually Lipschitz in a neighborhood of theta star, and that's enough for our purpose. So that's basically how our reduction works. And in the following, I will show some implications of this reduction. Basically, how it improves the regret bounds in some setups. So the best known regret bound for contextual linear bandits is this d square root t log t with the log t outside the square root. And the best known lower bound is has this square root has this log t under the square root. And there have been some attempts to improve this regret bound and remove this extra square root log t factor. And perhaps the tightest one is this second one, which removes the square root log t. but it adds some log t factors, and the resulting regret bound only holds in expectation. Using our reduction, we can basically generalize the square root t log t result from linear bandits to contextual bandits directly, improving this square root log t factor, and the result still holds with high probability. So another setup where our reduction helps is a batch learning setup. And in this setup, the learner is allowed to change the policy only a few times at pre-selected time instances. So in this case, the best known regret bound is loses this square root log d factor, and it only holds in expectation. We strengthen this result to a high probability bound and improve this square root log d factor.
Osama, just as a just slight motivation, provide some slight motivation on like where batch learning can be useful.
Yeah, that's a very good question. So um, one scenario where batch learning is useful, for example, if we have communication or computation constraints, for example, the entity that computes the policy is geographically separated from the where the system is deployed, so we may not want to update the policy frequently. Other setups may be due to some natural limitations, for example, in clinical trials or some ad clicks. We may have millions of feedbacks per second, and it may not be feasible to update the policy at each time instance. So that's where this batch learning may be required.
Cool, thank you.
The, yeah, so another setup where our reduction helps is this misspecified linear bandit, contextual linear bandit setup. Uh, and in this case, we can also improve this square root log t factor and strengthen the result to a high probability result. Uh, yeah, but our reduction adds this log t to the second term. This may be tighter or looser depending on the value of the misspecification epsilon. Another setup where the reduction provides some significant benefits in the grid bound is this contextual linear bandits with adversarial corruption, where there is an adversary that sits between the environment and the learner. The adversary observes the reward at time t, corrupts it in an arbitrary way, and the learner has access only to the corrupted rewards. In this case, the best known regret bound loses a lot of d factors, and we can improve these d factors by relying on the result for linear bandits. Um, yeah, so
I have
that.
a quick question here. How is this like? I mean, I guess one can consider corruption as a model misspecification as well, or not? Like, how are they related?
Yeah, you can think of this corruption as a model misspecification. However, there are some differences. So, for example, for the misspecification, the amount of misspecification for each arm is fixed throughout the time.
Hmm.
But in this adversarial corruption case, the learner may pick the first arm, the adversary adds some amount of corruption. The second time it doesn't add corruption at all. Third time it does like more amount of corruption. So the adversary has more power to manipulate the learner in this second scenario. Another setup is this contextual linear bandits with sparse unknown parameter. So in this setup, the unknown parameter may come from large dimensional space, but only a few entries of that parameter are non-zero. The problem is that we don't know which entries of those parameters are non-zero and which are zero. The best known regret bound for this case again loses its square root log t factor. We improve this factor, and we also provide the first batched algorithm that's nearly optimal for contextual linear bandits with the sparse unknown parameters.
Okay, quick question. Is this a computationally efficient algorithm?
Yeah, that's a very good question. So, for the sparse unknown parameters, there is no known computationally efficient algorithm that can solve this problem with this regret. Ours is also not computationally efficient in this case, but beyond the sparse case, our algorithm can actually be computationally efficient, and I will go through the details of this. Computational efficiency in a couple of slides.
Okay, thank you.
So another setup where this reduction may help is when we have distributed users in a communication constrained setup. So the learner is geographically separated from the users. The user has some context that it needs to convey to the learner at each time slot. But this context may be communication heavy. It may contain lots of information. And what our reduction shows is that if the learner knows the context distribution, then the users may not need to communicate the context at all in that case. Um and I won't go through the details of how this works, but if you are interested, I will be happy to discuss this offline. Yeah, so now let's move to the computational efficiency question. So the problem is that this action set x at each epoch is a very large set, and it may not be feasible to compute every action in this action set. However, this is not a problem that's specific to our case, but it's a problem that's related to contextual bandits with large action spaces in general, and people worked on this in the literature. And there has been work that shows that if we have access to a linear optimization oracle over the action set, then this is actually sufficient to solve the problem. And by a linear optimization oracle, we mean that if you give me one unknown parameter theta, then I can efficiently solve the problem argmax, the dot product of A and theta over A in the action set. Okay. So if we have such an oracle, then we can efficiently construct the linear bandit policy. So what we do in our reduction is given a linear optimization oracle for the original contextual linear bandit problem, we construct a linear optimization oracle for the reduced problem. So how do we do this? On a high level, if the unknown parameter set, so the unknown parameter set has some discretization, but let's for simplicity assume that we don't have this discretization, and the unknown parameter set is just a unit ball. So in this case, uh, uh, how do we solve this linear optimization problem? We want to maximize the dot product between x and theta for x in this set xm, and this set xm is just gm of theta tilde for all theta tilde in the unknown parameter theta. And by expanding the definition of this GM, we notice that actually the solution for this problem is simply theta. And that's because by definition of this GM, theta maximizes each term in this summation. So it will maximize the total summation. Okay, so what if we have this discretization in the unknown parameter set? Um, so if we have an arbitrary discretization, that may make the problem complicated. But if we do this discretization in some specific ways, then we may be able to solve this linear optimization problem. So one example is if we discretize the unknown parameter set according to this rule here. So we divide by some parameter epsilon that we can choose to be arbitrary small, and then take the floor of each coordinate, and then we do some denormalization. So that's one way of discretization that will work. And in this case, we can show that if we take the output of this discretized theta, then this will be a good approximate solution for this linear optimization problem. So as we said, this function g is not Lipschitz, but what we can show is that the dot product of g of theta tilde with theta as a function of theta tilde is actually Lipschitz in a neighborhood of theta.
Sorry,
And
remind us what was theta tilde?
yes, the theta tilde is this. Sorry. Yeah, theta tilde is this variable of the maximization problem. So this maximization problem of the dot product between x and theta can be written as this maximum over theta tilde belongs to theta of the dot product between gm of theta tilde and theta. So if we take this function, the dot product of gm of theta tilde and theta as a function of theta tilde, we can show that this is actually a Lipschitz function in a neighborhood of theta. And that's what makes this g of the discretized unknown parameter theta to be an approximate solution for this linear optimization problem. And in fact, this our reduction leads to the first computationally efficient batched algorithm for contextual linear bandits with large action spaces. And this we show in our NeurIPS 2023 paper. And we show this by first constructing an efficient batched algorithm for linear bandits with large action spaces, and then we use the described reduction with the approximate linear optimization oracle that we just mentioned to extend the algorithm to the contextual linear bandit case. And I'm looking forward to discussing this with you in this and yours.
Osama, sorry. So this, sorry. So previously, from previous slides, you were showing that it can be implemented if computationally efficiently if you have Oracle access.
Yeah, if
And
we have.
here, is it still you're still using Oracle here in this last slide?
Yes, exactly. Yeah,
I
we are still
see.
using an oracle.
Yeah,
And
I just didn't catch what was the difference here. You have yeah. What was the difference in this one?
so the main you mean for this NeurIPS paper, right?
Yeah. How is it? You already had this batch version, and you explained that this can be implemented efficiently if you have Oracle access.
Yeah,
But
that's a very.
how is this one different? Sorry. Yeah.
Yeah, so the main contribution for this paper is that we previously didn't have an efficient batched algorithm for linear bandits. So if we have an Oracle efficient batched algorithm for linear bandits, then it can be extended using this reduction to contextual bandits. But we didn't have that previously. And the main contribution in our NeurIPS paper is to provide such a efficient algorithm for linear bandits, and yeah, and then the reduction will do this extension to the contextual case.
I see. For linear bandits, you can usually use elimination algorithms, and I thought that would be a batch algorithm and efficient. No.
It is, but so we are talking here about large action spaces.
Oh,
To do this elimination, we need a linear scan of the action set.
right, right.
Uh, but if it's, for example, infinite or has exponentially many actions, like for example t to the power d, if we are doing some discretization,
I
then
see.
this may require a lot of time. But by performing this algorithm, we actually need just the complexity is only logarithmic in the number of actions
I see. So this is, but is it, am I right that that's still with the Oracle access?
with the Oracle axis. Yeah.
Yeah, yeah, yeah. Okay, okay.
Yeah.
Thank you.
So, and we believe that this Oracle axis is a reasonable assumption because even if we perfectly know the unknown parameter theta star, we need to solve this maximization problem
I
to
see.
minimize the regrets.
Yeah, thank you.
Yeah, so this is basically all what I have for today, and I'm happy to get questions.
I asked the question in the chat. Yeah, the contextual just look very much like MDP. Yeah, what's the difference?
Yeah, that's a good question. So the main difference between contextual bandits and MTPs is that the action that we take at time t doesn't affect the context at the next time step. For MTPs, the action that we take may affect our transition to the next step. But for contextual bandits, no matter which action we take, this transition to a different context is not related.
Okay, so the contextual it just changes by itself. Okay,
Exactly.
independent of actions. Okay, yeah.
Yeah, exactly. You can think of it like this.
Okay, thank you.
Okay. Do you like? I mean, you have all these theoretical achievements, and assuming Oracle access, like, is there? Do you have any thoughts on, say you want to take inspiration from your theoretical developments and develop a practical version of the algorithms? Have you thought about any inspirations we can take it in the practical situations?
Yeah, that's a very good point. So we are actually currently working on this, implementing this algorithm in like for practical scenarios. So we have some preliminary results, but it's still an ongoing work.
Right, right, right. I guess like for argmax Oracle, you can use like maximum inner product search. Like
Yeah,
it's just one of those like locality sensitive hashing type search method, right?
yeah, that's a very good point.
Cool. Have you thought about like extending those to pure exploration setups?
I'm sorry, could you
Right, right. So there's like regret minimization setup, but there's also pure exploration setup, like
yeah, the pure
a pack
exploration.
setup, that kind of thing, right? Have you thought about extending it to there?
Yeah, we actually didn't think about that, but I think that would be a very interesting future direction.
Yeah, there's a paper by uh, uh, Andrew Wagenmaker and Kevin Jamieson on doing this pack um, analysis for contextual bandits, but it's for generic policy class.
Hmm.
But they try to identify instance optimality there. But they also show some reduction to linear bandits.
I see, I see.
That's an interesting sort of related work.
Yeah, that's actually very interesting. Yeah, we will definitely check that. Yeah.
Sorry, may I ask a question also?
Sure.
Yeah, when you explain how to create the set of actions X at the very beginning for very basic setting, just to reduction from contextual bandits to linear bandits, you showed an example where you like just with the two thetas. Like, yeah, this example, when you have theta 1 and theta 2. But in general case, how is this capital theta set constructed? So is it finite? Is it infinite? And is it, if it's infinite, what's next? Is it still applicable there, or could you please elaborate on this?
Yeah, so usually people assume that this unknown parameter set is part of some bounded norm ball. Okay? So even if you don't know the set, you can assume it's the whole bounded norm ball. Okay? And your question is valid that if it's an infinite set, then we may not be able to enumerate all the actions in this action set. But we actually don't need to do that. So you can think of it as like we this X is something for notation purposes, but to actually implement the algorithm in the infinite or large action cases, we just need the linear optimization oracle over that set, which we explained how to construct towards the end of this here. So basically, it has been shown in the literature that if you have an access to a linear optimization oracle over the action set, then you can efficiently construct a good policy for the linear bandit problem without having to examine all the actions in this large action set. So that's basically how we do it if the action set is large.
And is this linear oracle builds up? Does this linear oracle build this theta d set with which you are working later on?
Yeah. So are you asking about the set XM or the set theta d?
No, I was asking about what exactly does the regression oracle do?
Yeah, so the regression oracle basically solves this problem here. So you give an input theta, any theta, in the unknown parameter set, and you are interested in the action that maximizes the dot product with this theta. Okay? And you are interested in doing this maximization over the action set XM. So that's a problem, and it's equivalent to doing this maximization over theta tilde in the unknown parameter set theta of this dot product between, because this action x can be written as g of theta tilde for some theta tilde. Okay, so this is the problem we are interested in solving, or that's required to get the policy. And one way to solve this is doing this careful discretization. And then if you take g of this discretization, it's an approximate solution of the problem.
Okay, yeah, I see. Yeah, thank you very much.
No, thank you for the question.
I also have some other questions. In your paper, in the intro somewhere, you mentioned that there's some explanation on why like adversarial context is much harder than the stochastic one. And in the paper, it was saying like, you know, you will describe it. I didn't read it yet, but I wonder if, I know you try to provide it at the beginning, but I didn't catch much from there. So do you have anything to, maybe a little more elaboration on that one?
Yeah, so basically when we were looking at the literature before writing this paper, we noticed some results for contextual bandits with distributional contexts that are not achievable for the case when the contexts are adversarial. For example, if we look at batch learning, we can solve linear bandits with order optimal regret in log t batches. Okay? We can do the same for contextual bandits if the contexts come from a distribution, but we cannot do this if the contexts are adversarial. And and we saw our reduction as something that explains this phenomena. Why all these good results for linear bandits achievable for contextual bandits when the context is generated from a distribution, but some of them may not extend when the contexts are adversarial.
Yeah, right. Right. But what if you forget about the batch perspective? Is it, let's say that, we don't worry about the batch setting, then what's the challenge that blocks us from like getting this removing this polylog t, like polylog t?
Yeah,
Like,
so that's yeah. So if we don't have any constraint, then we're actually not sure yet about the best regret bound for contextual bandits with adversarial contexts. Like, is this added log t fundamental? Probably
yeah,
not, but nobody knows yet. Yeah. Yeah, but without any restrictions. Yeah, we didn't mean that. Yeah, by this sentence we meant.
right.
Like this constrained those constrained setups of
Yeah,
contextual bandits.
right. And am I right that in the um, if you set the high probability bound, when you get the high probability bound, if you set delta to be not 1 over t, or if you set just delta to be delta, then does your algorithm not have log t at all?
It actually has this log t divided by delta. So if you choose
Oh, I
delta to be 1 over poly t, you don't. It's still the same order regress.
right. Yeah. Yuan Zhou had this paper that like you cannot get rid of this log t, like, and that's not about this, delta, but it was about something about this. There's like some worst case context that's
Yeah,
coming,
yeah.
and
Yeah.
yeah,
I know that paper. Yeah, it's the
yeah,
cold paper.
right. Yeah, cool. Yeah. And okay, I don't want to be like blocking anyone's question, but just you had achieved quite a bit of improvement upon the existing adversarial, corruption result. And okay, I haven't looked into that setting yet, but I think I know the algorithm. I think I improved the regret bound of that algorithm. That's via whole thing, right? But I was wondering, yeah, what's the like really the challenge in getting that adversarial corruption bound? Like, if you just do standard linear CB or awful type algorithm, then like why is it so difficult? Like, I don't know if it's easy, but yeah, I just want to hear if you have any intuition or thoughts about that.
Yeah, for linear CB, the challenge is in modifying this confidence bounds at each time step. Uh, so especially if the adversary has power to observe the history, so it's not like a fixed corruption. It becomes challenging to generalize this confidence bound, because maybe at the current time slot the adversary will put a large amount of corruption.
Right.
And one more challenge is that actually these algorithms that I cite they regret, they assume that they have no knowledge about the amount of corruption.
Right.
So if we have knowledge about the amount of corruption, then it becomes easier to modify these confidence
Right.
bounds. Yeah. That's the main challenge, that we
Right.
don't know the amount of corruption, then it becomes hard to
Yeah.
by the confidence bounds. And
Right.
it's actually shown in the literature that to get to get rid of the linear regret, if you don't know the amount of corruption, then the algorithm has to be randomized. We cannot have some deterministic rule of deciding, like we say at this time slot we will play this action. It has to be some probability distribution.
I see. But VOFO does achieve some bound and it's not randomized. And so I don't know, maybe I missed something, but yeah. What do you think about that?
If the amount of corruption is known, then
Oh, I see.
that may be feasible. But if you don't know the amount of corruption and you want some algorithm that if the amount of corruption is small, then it works well. If it's large, then it adapts to that.
Okay, so the VRFL based algorithm, you're saying that's assuming knowledge of the corruption?
Yeah, yeah.
Okay, got it. Okay, and in your work, you are assuming knowledge of that?
And we don't assume knowledge of the corruption. So basically, what our result does is, so this is the best known result for contextual linear bandits with, for linear bandits with adversarial corruption, the one on the right.
Mhm.
Our reduction just lifts this to the contextual case. And this result for linear bandits assumes that C may not be known.
Okay, and so my next question is what makes it so easy for your algorithm, right? That it's hard to achieve from other algorithm, and you're not doing randomization either, I thought.
Yeah. So so what our reduction does is that it shifts this exploitation problem to the linear bandit side.
Right.
So yeah, that's the main challenge. So how do we do this exploitation? How do we balance this? It's maybe challenging to do for contextual bandits with the changing action sets, but we move this problem to the linear bandit side that has a fixed action set. You do this, you balance this exploitation with the presence of corruption on the linear bandit side, and then we show that you will basically suffer the same regret.
I see. So it's because of the reduction. So in general, for contextual case, if you want to solve it directly, then you have to consider like randomization.
Yeah, you still have to consider randomization for the linear bandit algorithm, but
Okay.
yeah, but the algorithms are simpler, and the very great analysis is simpler for the linear bandit case.
Cool. Yeah, there's a question from Jiafan. What is the power of the adversary here, strong or weaker? Is it possible for the adversary to observe action before correction?
Yeah, okay. So I'm sorry I didn't go into like all the details of this adversarial corruption model, but I can give you more details. So the adversary model here is that the adversary can observe all the history of interaction between the learner and the environment. It can observe a pool of rewards in the current time slot from all actions. So basically, the adversary has access to rewards from all actions. It corrupts all of these rewards, and then the learner picks some action, and then it only sees the corrupted reward of that action. So that's the adversary model that we are working with.
Okay, so you mean that the learner may use a random policy, so the agent can see the reward for all action, but they may see the random policy, but they cannot observe the action generated from the random policy before the corruption, right? You mean that?
Exactly, yeah. So if the algorithm, as a function of the history, if the algorithm is deterministic, then the adversary will know the exact action that the learner will pick, and in that case, it can do much more corruption.
Okay, if you consider for this setting, I think there exists some previous work also studied this. Maybe I call it a weak adversarial. It's from Professor Chen Yu. It's a model selection approach for corrupting robust RL. I think they achieve a similar result. So, what's your improvement compared with this work? I'm not pretty sure about that.
So let me see. So it's a different paper from this one. So
Yeah, I think you also mentioned in the table, in the maybe you can turn to the further several page in the slides. Yeah.
Are you referring about to the paper or the slide?
Yeah, your slides here. Maybe you can turn. Maybe at the beginning you show a table for the result compared with previous work.
Yeah. So are you referring to about this one or?
Oh yeah, you mean that this will consider for linear? Oh yeah, I think there is this red t plus d2. Yeah, I think.
So I'm not sure, or maybe on top of my mind, I don't remember the result of this model selection approach. So maybe we can discuss that offline. But what we show here is the result for this for the adversary model that I just mentioned, which is that it doesn't observe the current action. It only observes the history and all a pool of rewards from all actions at the current time slot. So the adversary model that you mentioned is stronger, which is to observe the current action. But it has been shown that under this stronger adversary model, you cannot avoid linear regret in some cases. For example, if the bar of the adversary exceeds this omega d square root t, then you cannot avoid linear regret in this case.
Okay, that's interesting.
But under this weaker adversary model, you can still, for example, if the adversary bar is to t to the 3/4, you can still get some sublinear regret in that case.
Oh, okay, great.
I'm not sure if that answered your question, but
I think it's a great answer. Yeah.
Thank you.
Thank you.
Thank you.
Okay, so I'll stop recording the talk now, and yeah, you guys can carry on discussing thereafter.